All right, guys, let's get going. Let's see. Sally, he's excused today. Kayla? Mason? Zach? I think he still has something. All right, I'm gonna have a full day for him anyway. Riley? Jaylianne? Valerie? Katie? Dakota? Dalton? Dawson? Olivia? Nate?
Oh, here.
Robinson? Mandy? Sharon? Alston.
Yeah.
Took a while to respond. Before we start, I'm not making this a promise, but on a best effort basis. As you know, I record the lectures and I divide them into little pieces and put them on YouTube. And I give those to you in a YouTube playlist. I'm gonna add descriptions of what we've done that day as well, but if you wanna go back, just hit that playlist. It just comes up. It's typically 6 pieces. It doesn't let me do anything above 15 minutes. And I also have my handwritten notes as a PDF, as well as the Excel file I produced that day. Okay? Now, last time we developed templates for present and future value of annuities, and we use those to solve some simple, some complicated problems very quickly. Now we're gonna extend that, and we're gonna allow a certain rate of growth in those payments. So we're gonna calculate present value and future value of growing annuities. What we mean by that the first payment is $C, let's call it 1. Then each period payments grow at a constant rate of G. We're gonna make sure that G is less than the discount rate. That's because the formula we use is actually based on infinite series. That infinite series does not converge unless growth rate is less than the discount rate. Doesn't mean we can't handle it, but we can't do it using just the formula. But when we are implementing it, we will allow any growth rate. And assuming, come on. assuming the growth rate is less than R, present value of growing annuity, and I'm going to call that PVGA, is equal to the first payment divided by R minus G, and let's also add a balloon payment. One minus 1 plus G over okay. It is an ugly formula. Future value of a growing annuity with beginning payment I'm going to call that FVGA, bless you, that's going to equal $C1 R minus G times 1 plus R raised to the power T minus 1 plus G raised to the power T plus times. What I basically did, I took this portion first, the present value that is due to the annuity itself, multiply that with 1 plus R raised to the power T. That's basically the future value of that piece. Then I added future value of the initial money. Okay, these formulas apply only if growth rate is less than discount rate. If G is greater than R, which is going to be rare, since there are a finite number of terms, the present value and thus the future value are properly defined. I'm going to call this A1 plus A2, where A2 is simply present value of the balloon, and actually let me calculate it. This A0 let's call that PVB, present value of the balloon, you probably have guessed those are going to be the present value of the payments other than the balloon in each period, where AJ equals CJ divided by 1 plus R raised to the power J, where CJ equals C1 times 1 plus G raised to the power J minus 1. Alternative speaking, or C1 over 1 plus G now from this you can actually figure out AJ plus 1 equals which you can recognize that AJ times so we can go ahead and calculate it rather quickly. All right. You're probably thinking, there's way too many calculations, how are we going to do a template? First, we're going to actually write our own function in Excel. Just like the PV function, I'm going to write a function called PVGA. That's going to have inputs as, discount rates, first payments, the length, and the balloon payment, in addition to frequency of compounding, and we go from there. For that, we are going to use, I'm going to actually, in order to illustrate some simple techniques, I'm going to use the second method to actually write that function.